Hey friends, MoNaCo here. We are starting our second to last unit of study, organic chemistry. This is our first lecture video. At the end of this video, what I need you to do is understand how the carbon behaves. Also understand some basic properties of hydrocarbons and organic compounds. And you'll be able to recognize the three types of organic formula notations. This unit is heavy on the notations. How we show things going on paper is what we're going to really be doing a lot of. Organic chemical compounds are all around us, but we're going to focus on what their basic properties and structures are. Organic chemistry is kind of like a tree, okay? It's like there's many different branches to it. We're going to be focusing on the basics, okay? We're not going to be talking about things like proteins or DNA, which are definitely organic compounds. We're going to study the basics of the structure, nomenclature, and functional groups that are in every organic compound. We're not going into the depths of why the brain works or how the brain works, but we're touching on the very surface of what makes organic compounds special in this particular unit. Organic chemistry is the study of compounds that contain carbon and hydrogen. Pretty simple there. Carbon and hydrogen can come together in a few different ways because carbon's very special. It has 4 valence electrons, which means that it can form up to 4 chemical covalent bonds. This makes carbon have a funky shape. We call it a tetrahedron. It's not a pyramid. I know it looks like a pyramid, but it's a three-dimensional, three-sided pyramid, a four-sided pyramid, pardon me. Tetra means 4. Which makes it important for chemical structures. These things are not flat, they're three-dimensional. On paper, we draw them in 2 dimensions, of course, but you got to keep in mind, carbon is actually making a 3-dimensional structure. Carbon atoms share electrons with other carbon atoms because they're both nonmetals. It makes covalent chains, rings, and networks. Carbon is like a single link in a chain. Carbon, you can make a chain that's 2 links long. You can make a chain that's 2 million links long. That's why organic chemistry is so complex. These chains, rings, and networks that carbon can make get really complex, and that's why we have all this diversity of different organic compounds. 2 carbon atoms can share up to 3 pairs of electrons. Basically, carbon can do single bonds with its neighbors, it can do double bonds with its neighbors, and it can do triple bonds with its neighbors, which makes things much more complex indeed. Each shared pair of electrons is represented by a dash line. So we got single, double, and triple bonds, another level of complexity. And let's move on to hydrocarbons. Organic molecules that are only carbon and hydrogen. A saturated hydrocarbon is one where all single bonds between the carbon atoms, their maximum number of hydrogen is held by the carbon chain. A single dashed line, carbon-carbon, is a single bond. 1 shared pair of electrons per 2 electrons total make up the bond that is present, carbon-carbon. So in each one of these, we have 2 electrons in the carbons. Every single dashed line is 2 electrons, and if you count them up, we're obeying the octet rule that we studied earlier in the year, so that's a good thing. Counting up the octet rule for carbon, and hydrogen has the 2 that it prefers. Unsaturated hydrocarbons are ones that have multiple bonds in the carbon chain, like 2 dashed lines. Okay, it's like a double bond. 2 shared pairs of electrons for 4 total electrons make up those carbon-carbon double bonds. So if we count them here, we got 1, 2, 3, 4 electrons in the double bond. We'll notice here that this chain of carbons is not filled up with hydrogen. That's why we call it unsaturated. We'd have to break the double bond here and fill it up with hydrogens, and we make it saturated. Now, 3 dashed lines, again, unsaturated hydrocarbon, is a triple bond. 3 shared pairs of electrons total. If we're looking here at the very bottom, we got 2 electrons for each dashed line. While all of these carbon chains had 3 carbons in it, as you become more unsaturated, the number of hydrogens, drops. So while our first formula was C3H8, Our second formula was just C3H6, and our third is just C3H4. Okay, so the number of hydrogen goes down, carbon stays the same. You have more and more levels of unsaturated things. Properties of organic compounds. First things first. Bonding. They're always covalent or molecular. Those are synonyms. It's always a nonmetal and a nonmetal. Solubility of organic compounds. Most are insoluble in water, meaning they do not dissolve. Generally, nonpolar type substances. So oil is a organic compound. It does not dissolve in water because it does not follow the like dissolves like rule. Polar plus polar, nonpolar plus nonpolar. Conductivity, organic compounds. Most are not conductors, solid, liquid, or aqueous. These things do not create ions when they're in solution. They're not electrolytes. There's one exception, of course, organic acids, but those are really, really weak, poor conductors. That's like vinegar. Doesn't conduct electricity very well. Generally speaking, they follow the properties of covalent compounds, very low melting and boiling points because they have weak IMFs, intermolecular forces, low melting points and boiling points. Reactivity rate, we did a little bit of this in kinetics when we talked about the nature of compounds leading to the speed with which something reacts. Covalent compounds are slower. Organics are a type of covalent compound, so they react slowly because they have usually more numbers of bonds between the carbons and the hydrogens, so it requires more steps to break all those bonds, and therefore the reactions take longer. Now, the types of chemical formulas is really where we're going to get into a lot of our other notes videos. There's molecular, structural, and condensed formulas. Molecular formulas are the most common. Let's see if that disappears. It shows the number of atoms of each type of element in a compound. It's the least informative formula, aside from the fact that it tells you exactly how many carbons and hydrogens and nitrogens and oxygens are in there. So this is a molecular formula. For the molecule propane, you have 3 carbons and 8 hydrogens. Doesn't tell you much more than that. Structural formula shows the number of atoms of each type of element and how they're arranged and the bonds. This is the most informative formula. So the same propane, C3H8 from above, is shown here in actual structure formula. You can see the 3 carbons are in a chain, blink, 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 like that, and the hydrogens are arranged all around it. There's no double or triple bonds. So this is the most informative. Now, let's go on to the condensed formula. It's kind of like a hybrid between the structural and the molecular formula. These are useful. It's a combination of both the structural and the molecular formula. Generally speaking, though, it's kind of like a little bit of a roadmap. This is telling you that from the left to the right is kind of, we read these like a book. The first part of this chain is a C with 3 H's around it. The second one is a C with an H above and below. And the third one is a C with 3 H's around it as well. So from the condensed formula, I can figure out the structural formula, and I can also figure out that it's C3H8 I'm still talking about. But it's not as informative as you might think. The only place we really see condensed formulas is on table R in our reference tables. Let's move on here a little bit. Open-chained hydrocarbons. These are called aliphatic hydrocarbons. They're just straight up open chains. And when you look at these things, we first go for the molecular formula. How many carbons do I have in the chain? C6. And then how many hydrogens do I have? 2, 4, 6, 8, 10, 12, 14. C6H14. That is the molecular formula. The condensed formula, all you do is you take it 1 carbon chunk at a time. And you just kind of write it as it goes. Doink, 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 doink. All right, almost in there. So I've got 1, 2, 3, 4, 5, 6 carbon chunks. So the first carbon chunk is going to show like this, CH3, what I first put in the box. The next, the second through fifth one are just CH2. 4 in the middle there, so CH2 one more time. And then the last on the end of the chain is another CH3. I personally prefer molecular formulas over condensed formulas. So check out the second example. This one's on you. I want to see you do this one. You do that one. So there's 2 blanks there. Now the third one, molecular formula, I also want to see you do that one. But I'm going to help you out with the condensed formula here because it's a little bit different. Don't let this double bond scare you. All we're really doing is we're still blocking out bicarbons the sections of the molecule. So we go CH3, that's the far section. We got a CH2 after that. Then we have a CH, CH, and a CH2, and finally we're finishing with the CH3. So I want to see you do the molecular formula on that one. Let's see what we got next. Closed chains. These are aromatic compounds. So when you take one end of a carbon chain and connect it back to its beginning, you get a ring. So we just covered chains. We're going to talk a little bit about rings, and then there's more complex networks that can happen too, but we're really not going to see any of those in our work. So the molecular formula here, notice we're not asking for a condensed formula because where do you start? Where do you end? The condensed formula would have to be a circle, and that's not how it works. So the only case we're going to use here is molecular formula. I want to see you do this. And usually you just got to start by counting the carbons. 6 carbons, and then count the hydrogens up. See what you got. C something, H something. That's all there is to it. Couple notes. When drawing organic compounds, you must always have 8 electrons around each atom. We're going to be drawing a lot of these in our classwork and practice, so we'll get a hang of that. Hydrogen's always the exception. It has 2 electrons around it instead of the full 8. What else we got here? So at this point, I'm not expecting you to be an organic chemistry whiz. I should expect that you have a basic understanding of what carbon is, how it can do chains, rings, and more complex structures in organic compounds. Understand that hydrocarbons have some pretty simple basic structures and properties. Organic compounds are also a whole class of this thing. And recognize the 3 types of organic formula notations: structural, molecular, and condensed formulas. There's only about a half-page practice so far, and not a quiz yet. So thank you for watching. Oh my gosh.